So the title of this talk is Quantum Relational Hoare Logic towards a Formalization. So I will tell you a bit about what quantum relational Hoare logic is, and then I will tell you a bit about the efforts towards actually fully formalizing it, which has also, I think, a lot of implications on other Hoare logics when you want to formalize them. So, rough overview. First I will tell you why we study quantum relational Hoare logic, how it's defined and so on. Say a little bit about extensions, or maybe not, time is a bit short. Then I will tell you about practically working with qRHL, and so not just having the rules on paper, but you want to actually prove non-trivial things. So there's a tool we have, and I will tell you about some of the challenges, and then say a bit about the progress of the formalization. So, for the motivation, the main motivation for us to study qRHL, though maybe there may be many others, is post-quantum and quantum cryptography. So quantum computers threaten cryptographic systems, RSA, elliptic curve cryptography, etc. They all will be broken by quantum computers. On the other hand, quantum communication can give us better cryptography. So altogether, combining cryptography and quantum is a worthwhile thing, and we need security proofs when we do that. We want to know that our systems are secure, and especially when quantum is involved, everything gets non-intuitive, so we really want to have very rigorous mathematical security proofs. And the usual way how cryptographers nowadays make security proofs, it's not without exception, but it's the most common way, is the so-called sequence of games. So what you do in a sequence of games is you write down the setting you have, like the protocol you're analyzing, together with a procedure that calls the adversary and so on, and with a kind of if statement in the end that tells us whether the adversary won or not in attacking. So you write all this down, and your goal is to show that the probability of attack is low in the simplest case. And then what you do is you rewrite this game in a bunch of steps, and each time you just change a little bit, and in the end you get something where things are trivial. So maybe some program where just by dead code analysis you can see that there's no way to reach the I have successfully attacked point or something like this. And what you need to do is, between each two steps, you need to say that the probability of an attack has not changed. Or if it has changed, like, well, say it's upper bounded, lower bounded, changed by a certain number and so on. And if you combine all this, you know that the probability of attack here will also be very small. And there are two big problems if we want to formalize this. First is, how do we prove the relationship between two consecutive games? Cryptographers on paper usually say it's obvious, which is dangerous. And the second is, how do we find the sequence of games? And there are basically two approaches to do this. One is the approach taken by the cryptography tool, which rewrites the game with a set of rewrite rules, heuristically with some backtracking and so on, hoping to reach a nice game. Advantage is that it finds the sequence of games on its own, but the power is more limited, because if it doesn't, then it gets tricky. And then more popular is the EasyCrypt approach, where the user of the tool manually writes down all the games in the proof, and then manually proves the equivalences between two games in what is called a relational Hoare logic. So we use relational Hoare logic to show that two programs stand in a certain relationship, and cryptography is the big motivator for that. This approach is a lot of hard work, because it's not automatic, but it's a lot more powerful, and we are following this approach when we go to the quantum setting. So what is relational Hoare logic? So before we go to the quantum setting, we need to understand what relational Hoare logic even is. So it describes the relationship between two programs More specifically, it tells us how the variables, or the contents of the variables, of the two programs relate before and after the execution of the two programs. Where, since we have two programs, they are non-trivial definitional challenges, as what we mean by the state of the two programs, if we actually don't plan to execute them together, but let's not bother with that at the moment. And a probabilistic variant of this, so here this is some deterministic example, is used in easy code. So let's try to understand what this thing here means. So it means if, so that the first program has a variable x, the second has z and y, and what we claim here, if x is equal y, it's just classical variable, so this is a well-defined thing, and we run the first program which increases x, and in the second program we assign y to z, then afterwards x will be 1 bigger than z. So that's not too surprising with these two programs, but you can have much more complicated games in between that do very different things. And, well, the nice thing is that you can break down your reasoning to reasoning about individual steps. So here's another example where we want to show that if two variables are equal, and the first game increases x twice by 1, and the second increases x by 2, then they are also equal afterwards. I mean, it's not too surprising, but you would like break it down into little steps. So first x1 equals x2, we do an increase on one side, a skip on the other, which gives us then x1 minus 1 is x2 by rules by basic rules for assignment. And then we do this again, we get this formula. Now we do something on the other side, which does a substitution on the x2, and we get this formula, which simplifies to x1 equal x2. And at least for such a simple game, this can be fully mechanical. I mean, this is just syntactic application from rules, and this is, I mean, most simplifiers should be able to simplify this last step. So now we know what relational Hoare logic is, and we have an idea about the motivation. So what do we do in the quantum setting? Now the problem in the quantum setting is that we cannot just reuse probabilistic relational Hoare logic. Because now our games, our programs, contain quantum variables. And they can perform quantum operations. So in the simplest case that you have when you analyze post-quantum cryptography, you have that there's an adversary who has an internal quantum state, and you don't know what it does with that, but it's represented by some quantum variable of suitable size. In more complex situations, even your protocol is actively performing quantum operations, maybe in order to send quantum data over the network, etc. So we need a new version of relational Hoare logic that supports quantum things. And this is quantum relational Hoare logic. So, what are the features of quantum relational Hoare logic? I don't want to go into the full precise definitions of all the things. I'm trying to first give you an idea what these judgments look like. So, as before, we have a precondition, a postcondition, and two programs. And now the difference is that these two programs, they can contain quantum operations. So in this example, they just both apply the same transformation to their respective variable. And then we can have some preconditions that may also involve talking about the variables. So in this case, it says if x equals y, and we apply the same transformation to both, then x equals y afterwards. So shouldn't seem too surprising, but it's not actually a trivial thing to even define this. Why is this non-trivial? Well, first question you have to ask yourself, what does it even mean that x equals y when we're talking about quantum variables? Because with classical variables, it's very easy. I mean, operationally, we could say we test equality by just taking one variable, taking the other, the value from it, doing an equality check, and outputting a Boolean value. Quantumly, this is not so easy. We can't just take the values, because looking at the values changes the state. And not only is it not something that we can actually implement, it's actually definitionally not meaningful to talk about the content of this variable or the content of that variable, because they may be entangled with other parts of the system. And also, you have to ask, like, what does it mean to execute those two programs? So if we just say, well, we just execute them in parallel, then that doesn't give you the semantics you actually like, because, for example, if this is like a random choice, a random bit choice, and this is a random bit choice, then the probability that the two variables would be the same would be 1/2. But we want to express if it's the same program, then they should have the same output. So you need a definition that somehow syncs the two runs together. Yeah, and compared to the probabilistic setting, well, quite expectedly, the main source of trouble is the presence of entanglement and how to deal with all these things. Oh, yeah, I should have mentioned that. So what we put here is not something too difficult. It's just an elementary while language, so I think anyone kind of reasonably experienced with quantum programming would, when I say, give me an elementary while language, come up with a language that is more or less the same than that one. More interesting are the predicates. So the predicates are given as subspaces. So we have our quantum memory. We also have classical variables, but I will ignore them for now. So the quantum variables, they're in some quantum state, and our predicates are just arbitrary subspaces of the space of all memory contents. So I could write here anything I want, as long as it's a subspace of the space of all possible memory contents. Now, yeah?
Just a clarification. The variables are subspaces or relations are subspaces?
This whole thing is a subspace, and this is some pseudocode which we don't yet understand why this would represent a subspace. Yeah. So in general, I could write anything, but some things are quite difficult to write, and if I would write this out here as an explicit mathematical formula for a subspace, it would also be something you would not recognize anymore as a quality, which is why I'm using some syntactic sugar here. There, just to mention some of the challenges we encounter when we try to define it, like these are the two rules that are most challenging. One is the equal rule that says if x are all the free variables of the program and we run the same program, and x is the same on both sides before, then x is the same on both sides afterwards. Sounds very natural, but it's depending on how you define the logic and the equality, you may not get that. So you have to be very careful with that. And this is very important for saying, like, especially when you have adversaries, because you want to say if the adversary does the same thing in both programs, then this should not suddenly lead to a distinguishing between the two programs. Then we have the frame rule, which is also very important for modular reasoning. So if two programs lead from A to B, and then you intersect the subspace, which is intuitively the analog to a conjunction, with some other unrelated predicate R, then this predicate R will be preserved, as long as R does not talk about the variables in C and D. Again, very useful, but you can also lose that one for weird quantum entanglement reasons. So, let me show you how qRHL is actually defined. So what we do, if in case you know probabilistic relational Hoare logic, this will look familiar. What we say is, this thing here is interpreted as follows. We say for any two quantum states that are marginals of a state satisfying this predicate, so you take any state on pairs of memories, because this is a predicate on variables here and here, take any state on pairs of memories, you take the marginals, which means tracing out the part of the memory that we are not talking about. It's analogous to marginal distributions in the classical setting. So for the marginals of any state that satisfies the predicate, we run these two programs on their respective marginal states, and then we ask that the final states should be marginals of some state that satisfies the post condition. So that would be, wait, let me skip ahead. I show it again to you in a slightly different picture. So it says for any state rho that satisfies the precondition, we take the partial traces, we apply the semantics of the program, we get the final states, and we ask that there should be some rho prime that satisfies the precondition, postcondition, so that if we take the marginals, we get this back. So this is kind of a bit unintuitive, but it is a way that works very well in the probabilistic setting. And if you just, sorry, bad things happening. If you just do the same thing, so here we're back, in the quantum setting, you almost get a good definition, except you don't get, I think it was the equal rule, you don't get. So it turns out you need a slight tweak. You need to additionally require that this joint state is separable. There is no good intuition why you have to do that, except that then things work out much more smoothly. Without this, okay, it was the frame rule that we apparently don't have. So this was a rush through the definition of qRHL. If you didn't follow all of this, doesn't matter, it was just to give you an idea. But there's still another thing that should be mysterious on these things. It's what do we mean if we write, for example, x1 equal x2 if they are quantum variables. This is a priori not a meaningful thing. We need to interpret this as a subspace. If it's not a subspace, then like all the other operations will not really make sense anymore. So how can we define this? And it turns out that there is quite a simple definition of this, which in retrospect seems also relatively natural for being an equality. So the subspace x1 equal x2, so psi satisfies this assertion, meaning psi is an element of it, holds if and only if psi is invariant under swapping the registers x1 and x2. So if you take the unitary that swaps those two wires, if you think in terms of circuits, then this is the eigenspace of that unitary with eigenvalue 1. Yeah, so it's the thing, or the, I never know whether it's the fixed, the vectors that are fixed under it or invariant under it, but it's the vectors that on which the swapping unitary is the identity. This is a subspace. It's also a closed subspace. If things get infinite dimensional, we need to be careful with distinction between topologically closed and not closed, but in this talk I will just not get into any infinite dimensional details. Well, this definition works out fine, but it doesn't behave as intuitively as a classical equality. So you have to be also careful to prove whatever you claim and not just assume that it's nicely behaved. But at least it's reasonably behaved. That's, in the quantum setting, reasonably behaved is usually the best, we hope. Okay, I'm going to skip the extension slide and now come to using qRHL. So what happened after we had the definition and the basic rules? So we did, in order to work with qRHL, since you don't really want to do anything non-trivial by hand, because then you lose the whole advantage of being formal, namely having proofs that you trust. So we developed a tool for qRHL reasoning that we also used for one non-trivial crypto protocol. And here's a short overview of the architecture of this tool, because it's maybe a bit unusual. So we have a tool that is specifically programmed for qRHL, that has specific tactics for qRHL, more or less corresponding to the various basic rules, but with a bit of additional, like, making things nicer for the user, but more or less it corresponds to the various rules we have. And the verification conditions that you get from applying these rules, they're usually inequalities of subspaces. So you need to, if you use classical Hoare logic, usually your verification conditions are this predicate implies this predicate. Now we have this subspace is a subset of this subspace. So you get inequalities of subspaces, and instead of designing a whole, the whole mathematical framework in a new tool for reasoning about subspaces or even for expressing them and so on, what we did is we use Isabelle Hall as a backend for the tool, which means we like all the arbitrary formulas, like, okay, you can't probably see it, but here's like some formula here, some lambda term. This is just given to Isabelle and say, you parse it, you interpret it, which means we get all the power of Isabelle kind of directly, but still have the opportunity to write our own tactics specifically for the logic at hand. So basically there's this separation of powers. qRHL things are done by the tool. Verification conditions are handled by Isabelle, so you can then use Isabelle to reason about the verifications conditions, either with some tactics that are kind of just passed through, or you can just open a separate theory in Isabelle if it's a more complicated proof. And one advantage of this is that it gives us a smooth path towards full verification, because all we have to do is kind of fill in more and more of the stuff that is done here to send it to Isabelle and prove all the lemmas that are done in Isabelle, and that way we will eventually have something fully formalized. And then when you're working with things in practice, you run into various challenges. And from the usability point of view, the biggest challenge is what I already mentioned earlier, that the pre and post conditions are arbitrary subspaces. And similarly, like in the classical setting, you might say pre and post conditions are arbitrary predicates, or equivalently arbitrary sets. But that does not mean that you write them in actual set notation. You write lambda expressions, you have operators, quantifiers, and so on. And in the same way, we would like to be able to talk about subspaces in a way that makes things nicely readable or reasonably readable and compact, while still being just a syntactic sugar for defining subspaces. So here's an example of that. So this is a well-defined subspace definition. This is a screenshot from Isabelle, so this is exactly how it could be written. So let's try to understand this. And this is, I should mention, this is now something, even if you don't care about qRHL, if you care maybe about another Hoare logic or about any kind of way of how you would like to represent assertions in quantum programs, this is pretty much independent of the specific Hoare logic, the problems we have. So let's try to read what this says. So intuitively what I'm claiming here is the classical variable x is greater than 0, and the quantum variable contains cat x. Yeah, so this notation is quite suggestive. This cla means here what comes here is classical and so on. But in what way is that ever a subspace? Well, by clever syntactic sugar. So if we have x quantum equal something quantum equal x, what we actually mean is that the as a subspace, we say the content of Q is in the span of cat x. So we have span of cat x on the variable Q, tensor with the full Hilbert space on everything else. So this is what we mean by such a statement, but this thing gets completely unreadable very quickly, and it's not even really formally defined, because adding this index Q doesn't really have any formal meaning. It's more like, yeah, you get what I mean when I write this tensor product kind of notation. Then the other thing here we have, how can we, with a subspace, talk about classical variables? That's weird. Well, it's actually also quite simple once you have seen it. The thing is, the classical variables are not part of the quantum memory. They are kind of like fixed values that get substituted in here. And this so this thing is just a Boolean expression that is true or false, depending on whether x is greater than 0 or not. And this cla thing takes a Boolean and gives me the full space if the Boolean is true, and the 0 space if it's false. So, which means that this predicate here can be satisfied by a quantum state if and only if x greater 0. So effectively, it's a predicate about x and not about our quantum state. And then we have here intersection, which means roughly the same thing. So you can express a lot of things very conveniently with the right notation, and I would say this is these kind of things are one of the big challenges when you actually formalize your logic in a way, in a tool where you don't only want to say in the end, yeah, I have formalized it, but you want to do it in a way where you afterwards can say, I formalized it, and you can use it. You don't want to write expressions like this and if expressions like this and so on. But it turns out that there's still one thing that is quite hairy in these kind of things. Because we have to get from this expression to this. Or similarly, we may have something like C0 on variables Q and R, or a quantum equality between Q1 R1 and Q2 R2, all these things. And I've told you what this means, but I've put this kind of thing here. I've just said, well, it is just a space in this variable, and I don't really know what that means. Like, what is even a variable? I mean, if Q is a string, then I don't know what putting a string would be here, or if it's, so what is it? So we have to ask ourselves two questions. What is Q? So what is a variable? Like, what's the type of a variable? Is it just a index into a memory position? Is it something else? And then we've more complicated, what is like a list of variables? So here we specifically have this syntax to notationally distinguish, in order not to confuse Isabelle, between variables and tuples of variables, which we sometimes need because we apply operations to several things. And this is even could be a different type. This is not the same thing, and so on. So basically, the question is, how do we define variables and how do we talk and reason about quantum memory locations? And this is something we need to answer for all kinds of homologies. So the approach used in qRHL tool at the moment is the following. So first we define a variable, so the thing referred to by Q, roughly speaking as a pair of a name of the variable and a type. Now there's a big caveat, because this, if I would do it like this, I would need a dependently typed language, which Isabelle isn't. So we do some trickery to it's actually a pair of a name and a set with some cleverness around so that it looks like it contains a type. We package this in some type-safe way so that we actually have a type variable that depends on the type of its content. No need to try to understand these definitions. I'm just putting them there so that, oops, that you see a picture of it. So basically a variable is this thing with some nice wrapping around to make it type safe. A quantum memory is now can now be defined as so a classical memory would be a function from variable to value, where of course the value has to be of the type given by the variable. Again, we need to work a bit harder to make this in Isabelle because we don't have dependent function types. And then the quantum memory consists of all the states of this form, where the cat states contain classical memory content. So this is how you can do it. And now you can define something like apply a Hadamard to the variable Q by just kind of doing some index, the formulas are ugly, but you can define them. And then this type, so oops, before we had variable, and now what are variables? And turns out we need yet another type, because this thing is roughly speaking a tree of variables. Again, with a lot of extra trickery to make this type safe without having dependent types, but I'm also not going to go into that. And then you need to define all those operations, like if I have a variable tuple how can I interpret an operator on some space A when applied to variables of type A as an operator on memories. Yeah? Yeah. So these are the kinds of questions we need to ask ourselves, and the whole thing is not so pleasant in the end, I must say. So the experience is it is rather cumbersome to define. It is because even if you do this operator applying, you need to kind of reorder your space before you can apply it and so on, because the different variables are not necessarily continuous in the memory and so on. It's very tedious to reason about reordering of values, so actually like QR being in state cat01 should be the same as RQ being in state cat10, which is true, which is provable, but you need to do a lot of manual things to do that. Maybe this can be made better by nice optimization. Then you have generic reasoning is difficult. Like if you want to say something like, you don't want to write it down for concretely the variable q with the name q, but you want to make your statement kind of more general. This gets hairy because, for example, if you have a 2-bit variable and you apply C0 to it, or you have C0 applied to Q and R 1-bit variables, this is structurally a different thing, because this is not a tree and this is a tree and so on, and you cannot instantiate one with the other. There's a lot of ugly things happening. So there's definitely improvement needed in that direction, and this is something where we have work in progress using register formalism that I was also presenting last year at PLanQC', or PLanQC' it's called?
Yes.
Okay, apparently I never published at PLanQC', but at Planck. So register formalism is something to abstractly reason about memory locations which don't have to be continuous. They don't even have to be on a computational basis. You can refer to the regular register X in diagonal basis and so on. So now we, instead of having all these like detailed encoding things, we have something abstract. It's not really requiring that the memory is in a specific way as a superposition of dependent functions and so on. So you can get rid of a lot of messy details, become more abstract, while the definitions being actually even simpler, because a register in that sense is abstractly is just specified by mapping the operators on the variables, it should say variables here, to the whole memory, and that's satisfying some conditions, and that turns out to work very easily. So now let me tell you in the remaining 2 minutes, like what is the progress towards full verification. So the hardest work at the moment is the background theory, because we chose to not make the whole thing restricted to classical, to finite dimensional systems, because we believe that this is, at some point you want to talk about quantum integers and so on. So we try to have all the mathematics in place. So we have, we need to talk about infinite dimensional Hilbert spaces, bounded operators and so on, for reasoning about the predicates and the unitaries and so on. So we already have an Isabelle library for that. Then you need to talk about the tensor product. Tensor product of Hilbert spaces is easy, it's also done. But you need to talk about tensor products of operators and so on. And there's, I mean, I would dare to say that most people in this room will probably not even know all the mathematics kind of in a pen and paper way that are needed here if you do this carefully. I'm daring to say that because I didn't before I started this. So I'm just assuming I'm somewhere in the median here. Trace class operators also hard work. So this is both work in progress. And then you need to do the semantics and rules. We haven't even started on that because without the background theory, that's pointless. But even if you don't have this, this thing here would mean that all the reasoning about verification conditions is perfect. So that would be already a good, like, halfway point. And I hope to reach this point soon. So to give you like the kind of vision slide in the end. So what we have is we have the logic, we have a tool, and we have also one reasonable case study. And then we want automation procedures and improved logics and usability improvement, more protocols, and more usability, yeah, all this kind of oops stuff, sorry, yeah, just blah. Okay, thank you.